So somebody asked about critical values for test statistics and how to find them. What do they mean? So it's been a while since I've done a video like this, so I thought I'd record one this morning to try to help you out. So um, this is from the next three exercises that come from the cookbook exercises that I posted in week 8. No, week 9. No, it would have been week 10, I think. But they're one sample tests. And this is the directions I had on top of the cookbook exercise. And this is basically what you want to do. Check the conditions, state the claim, write the hypotheses, find the test statistic, find the p-value or the critical value. You don't need to do both, and we'll make a decision and write it in the context of the claim. That's when you're using Dr. Stevens' language or that flow chart. If you looked at my flow chart notes, my videos there, either works. So I don't know if I'm going to walk through. I don't know that I'm going to check the conditions. I will look at the claim and I ran I use software to generate all this stuff, but because the point of it is not how to run these tests, but how to make that decision with a critical value. So let's get rolling here. So this was about, let's see, this problem was about, let's see, producer processed orange juice is 20% or more of all juice drinkers prefer its product. So to test the claim, they sample 200. So let me get them do some writing here. So we know n equals 200. Out of those n people, 200 people, 33 of them preferred the brand. Looks like that's less than 20%, because wouldn't that be 20% of 200 be 40? So it's probably too high. So when I'm going to do a H1 and HO write down my claim. So the claim is we're gonna be the consumer group, and we're gonna or the competitor, and we're gonna say that we don't think their claim is correct. So we're gonna say that the true proportion of juice drinkers who like that other company's product is less than 20%. So the H1 will be the claim. So then I use the software to run the test, and I set it up as a left-tailed test, and that's what I got for the test statistic was the z equals negative 1.24. So now what if we want to find the critical value for z, because this is a z test. So this is a left-tailed test, so I'm going to look at that column. This is the very bottom of that normal curve table in Dr. Stevens' textbook, or that standard curve table. Um, and we'll get a left-tailed test, and it's a 10% level. So we're going to look at that number there. So is our test statistic less than our critical value? So here's what we've got going on. Here's the mean of 0 because we're on the standard normal curve here. Here's the negative 1.24. And in order to say that something statistically significant is going on, we're saying if you can get a test statistic that's less than negative 1.28, you can reject HO. And we can't reject HO because our test statistic isn't as far. This area to the left of the critical value for Z, that number there, is called the rejection region, which means you're going to reject HO. And we can't reject HO because the test statistic isn't in that region. So we're going to fail to reject HO. There's not enough data using Dr. Stevens' language. There's not enough data to verify or to defend the claim that um, there's not enough data to refute the claim that the 20% or more of the juice drinkers like that other product or something like that. Okay, so that's where this critical region, critical value in the rejection region. But you can also look at the p-value. See how that p-value? I know it's on my screen. It's a little small. I'm seeing 1.080. That is bigger than 10%, 0.1. So we'd fail to reject HO. It's not small enough p-value. So what I'm trying to do with pointing that out is you do not have to find the critical value and do the rejection region and find the p-value. I mean, p-value is pretty easy to find, so just go with that, unless I'm asking you to find the critical value for z. I won't ever ask you for t. Um, Certainly not on any test or quizzes from here on out. Okay, so that's for a left-tailed test. Now I've got one about this is again from those cookbook questions, and what are we seeing? We're seeing they're shipping, they're receiving shipments of Christmas tree light bulbs. This, according to the manufacturer, the stock is less than 10% of their bulbs will be defective. So they checked 56 bulbs and found that 9 had defects. So let's see, what p hat? P hat's equal to 9 over 56, which is, I don't have a calculator right here. Um, well, actually, I get the answer right here. that that's equal to about 0.1786. So almost more than 17%, which is a lot more than the 10% of defectives. So at least at that point estimate would show that it's something up. Now we're going to run the test. So basically, HO would be nope, the manufacturer's claim is correct that only 10% of the bulbs are defective. And this is just a bad sample of 56 bulbs. And then because we think that this is too low, right? Because that's a lot higher than our 10%. We're going to make this be a right tail test. And then we do our test statistics and everything. And of course, I did that here with that Rossman chance applet, and I clicked right tail, so I typed in. You know how to run this. So I typed in that, and there's my critical value of z. So my tested, I'm sorry, that's not my critical value of z. That's my test statistic. So the test statistic is 1.96. Now we're running what kind of test here? What level? A 1% level of significance test here, right? See that? So we're going to go in that little normal mini table here. I got to go back to blowing this up. So if we're going to do the critical value method, this is a right tail test, and we're going to do a 0.01, so 1%, 0.01. So that's the critical value of z. So here's the little normal curve. Here's 2.33, which is the critical value. And our test statistics isn't that far out. It didn't fall in the rejection region. So we're going to fail to reject HO again. Of course, we kind of knew that because, you look at that p-value. See, that p-value is bigger than 0.01, so it's not small enough. It's not far enough away from the middle to say something statistically significant is going on. Okay? And then we've got this one about television stations, and they said they used to be that 70% of the 70% of the TV watchers in that area watch their news at 11. They think it's changed. So this is going to be a two-tailed test. We don't know whether it's more than that or less than that. They just say it's changed. So what we're going to do is we've got 80 viewers and 60 watched, so p hat equals 60 over 80, which is 3/4, so 75%, which is more than 70, so something's up. I mean, at least that point estimate is higher, but we know we have to run statistical test to see if it's far enough away from the middle to say something's going on. So we're going to say the proportion equals 70. That's the old. And then we're going to say, because we don't know if it's increased or decreased, so we're going to make it be a two-tailed test. And then, of course, I let our Osman Chance run that for us. And let's see. So I got a z-score of less than 1. So as you probably know, that's going to be not statistically significant either. So, but we've got what level of significance they have us test at? They don't tell us. They don't give us a level of significance. So is somebody going to lose a lot of money if they say uh, yes, it's changed? Well, they might, because they might do something different with the programming. They might spend a lot of money in trying to improve the audience size when really they can't say that it's different, that it's changed, or maybe they think they want to change it, but they'd want to probably run a right-tailed test then, but not for this problem. So here's the normal curve here. Let's finish drawing this normal curve and finish that thought. So they didn't tell us a level of significance. They could lose a lot of money if they make the wrong decision, which they aren't going to hear. So let's go with the 1% level of significance. This is a two-tailed test. So what that means, negative 2.575 and positive 2.575 are the two cutoffs. So if our test statistic falls above that, or if it falls below that, we reject HO. But as we said already, a z-score of 0.98 is not even one standard deviation above the mean. Not in the rejection region. We're going to fail to reject HO. Fail, Dan, fail. Not enough data to uh, refute the claim that. Well, the claim was that the claim was here. I got getting myself in trouble. That I'm not identifying the claim. The claim would be HO because they think it's changed. The television stations think it's changed. So there's not enough data to support the claim that the audience share has changed or something like that. Okay, and then the chi-square because you asked me this during week 13. We're going to run a chi-square test, and of course it's a different test for a goodness of fit test, but it's the same thing. Oh, come on, Dan. Okay, so this came from the textbook. It's one of those your turn exercises, and when you're doing these chi-square tests for independence, HO and H1 are pretty easy to do. They're trying to say, is there a relationship between vehicle size and where people live? So HO would be, well, there's always no association. So there's no association. There's no difference, right? Association between uh, area the person lives in, area buyer lives in and vehicle size. Yeah, vehicle size. I think I misspelled that. And then H1, you can say there is an association. Notice I'm not saying correlation. Association, because these aren't quantitative variables. These are categorical variables. So there's no association. And let's see. They don't have a clear picture whether they want to know which is the claim. So test for a dependent relationship. So that would you mean there's an association? So let's make this be the claim. Let's make each one be the claim. So I could certainly run that by hand, but like what Dr. Stevens showed you, I also can run that calculator that I showed you how to use, and this is getting me a chi-square test statistic of 12.4714. And then, so what's the critical value for that? Well, chi-square distribution is not normal, but we're going to see how it's a right skewed distribution. But that chi-square value right here, see how that's a rejection region? Um, so the way you get the degrees of freedom with these two-way tables is you take your rows, and you probably know this. You take your number of rows minus 1 and your number of columns minus 1, and you multiply them. So in this case, it'll be 2 by 2. So we have 4 degrees of freedom here. So we only need to know this if we're going to go pull this off the table. So 4 degrees of freedom here. Where can I see this? Uh, 4 degrees of freedom is right there. This is a 5% level of significance. So we're looking at a critical value of 9.488. So let's see here. What do I want to do? I guess I'm going to do some erasing. So what we're looking at is here's our chi-square distribution. It was what? it was a 9.488 or something like that, and our test statistic is 12 something. So that is in the rejection region. So we're going to reject HO. There, this is a dependent relationship. And of course, if you look at what the calculator told me, there's the p-value at less than 5%. So reject HO, same deal. Okay, so remember, you don't have to find the critical value and the p-value. You only need to do one or the other, and then you can make your decision and continue on. Okay, hopefully this answers that question for you.